Good afternoon, first of all, and thanks for being here today. Premises, I'm not fluent, I'm not very confident with French, so I will be speaking in English to you. Hope that's not a problem. My name is Francesco MAJA, and I work for GF Machining Solutions, where I'm responsible for engineering within the additive manufacturing division. Now, as a very, very fast introduction, what is GF and what we do. It's a corporate with proudly over 200 years of history. We're actually split in three divisions. Piping systems is the oldest one, then casting solutions, and finally machining solutions, only 100 years old. We span across solutions for fluid transportation with piping systems. We cover a lot of cast products with casting solutions, and finally with machining solutions. We care about developing technologies that we offer to the market in the state of machinery. Overall, it's a company with around 4 billion turnover. As you see here, the figures from 2022 and over 15,000 employees worldwide. I forgot to say, but we're proud of that. It's a company established and still very headquartered in Switzerland, with all R&D's activities as well as production. Now, pertaining GF Machining Solutions, we are traditionally a world leader in conventional manufacturing, milling, and electro-discharge machining specifically. And through the years, we have expanded our portfolio into laser machinery as well, with laser texturing, structuring, and engraving machinery. And since 2018, additive manufacturing. Now, I believe that the history of our companies is important for you to understand what we're going to present here today. Additive manufacturing for us is a complementary technology to what is conventional manufacturing in order to achieve a final part. So we all know that additive is not a technology that in majority of cases gives you a final part. It gives you a raw part, and therefore the company decided to invest in additive manufacturing as a complementary technology that enables complex shaping, the possibility to handle complex and tough materials, at the same time completing what is done finishing on a conventional manufacturing machine. And this is what we mean by a full workflow that leads you to a final part that is according to drawing. Regarding AM, we are of course offering machines. That's in the middle of our offering portfolio there, and together with that we complement it with software, with application support, so expertise, materials in case. But I would like to focus on the bottom right quadrant, which is the integration. That's really the core of our know-how, and I can say also the uniqueness of our offering. Now, regarding the machinery itself, we have two types or two families of machines. The 350 platform that comes either in a flex or a factory solution with integrated powder management, and then a large machine that is called DMP Factory 500. On the first case, we cover 275 to 275 420 build size, and second case is 500 500 500. So you see, we're already oriented on the large, let me say, side of a full portfolio of parts you can make. where everything scales up. So the complexity of handling that part and therefore finishing it becomes more and more relevant, and the challenges, and the challenges together. One last word on this small introduction. As part of GF Group is also what we call casting solution additive manufacturing center. There it's actually a factory where we, together with them, it's a sister company, we established a park of machines that offer third-party manufacturing to the market. So it's I believe, a unique offering where you have a company that is either capable of offering you machinery or parts on demand, depending on what your requirement is. And that also makes a big difference in developing and growing on the technology side together, as you can not only develop machines, but as well develop the technology on real end user applications. Now, on the post-processing of metal parts, which is really the core of today's presentation, here's a breakdown of what not us, but our customers gives us as a feedback. So it's really the end user voice. What is the cost breakdown of a part done by, I'm talking about metal parts, of course, done by additive? Roughly it's 40% the process itself. This is, as you know, machine, powder, and operator time, labor, facility, all that pertains to printing itself, in very simple words. But then, as you get a part out of the machine, there is another 60% of costs that pile up and contribute to the cost per part of the final geometry that you intend to put in use. 30% is post-processing, and by post-processing we mean heat treatment, that we know is always there, moving from a simple stress relief into more complex heat treatment cycles like solution annealing and aging, like T6 for aluminums, etc. Hot isostatic pressing even, very lengthy and expensive. And then you have everything that pertains to support removal, machining, surface finish improvement. All of this is what we generally broaden called post-processing. And then you have final inspections that, depending on the criticality of the part, but they may also weigh a lot. If you think about X-ray, liquid penetrant, ultrasonic inspections, even CT scans in case. So as we talk about an expensive technology and users would like their parts to be less and less costly, the point of view of GF is, yes, we're working on more productive machines. We're working on lowering the cost of raw material, increasing the automation so that you have a less expensive process, or if you like, a lower cost per part at the printing side. But let us not forget about the other 60% of the story, which actually heavily contributes on the cost of a part. Now on the inspection costs, there is there we would need 1 day of presentation alone. But just as a brief mentioning, we are actually working on a method, an innovative method, to have in situ monitoring of your print quality directly on the part inside the additive machine. Of course, it's a long way together with the end users to bring it up to where we want it to be, meaning a qualified method that anybody accepts to directly check and quality ensure the part inside the machine, so that CT scan can be avoided. That's what that's the dream. No, that's where everybody wants to be, and we're confident we will get there. This is already, I think, well advanced, and for sure different from what is currently over there as a commercial offering, based on eddy current, which is a well-established technology in for conventional parts. We're porting it into the additive machine. So for those that are interested, definitely let's have a chat offline. Now on the post-processing side, what you see here, I think, is was a significant example of what we mean by that. This example is derived from motorsport. Of course, yes, budget is a topic as well there, but also lead time. We want to have the cheapest part possible that is compliant at the lowest cost possible. And when it comes to these complex shapes, where at the end the final drawing requires tight tolerances and good surface finishes on some areas, the question is, okay, what is the optimal workflow to achieve that? We started with this customer, this was Formula 1 customer, where the workflow was just printing the part and then figuring out a way on how to machine it. Ended up the part costed more to machine, just those small areas that you see there shiny are the ones machined. This part costed more to be machined than to be printed. Why? Because there's a lot of dedicated tooling and a lot of referencing operations on the milling machine that take up time, and therefore they take costs. What we did here was conceiving the workflow in a way that you could directly machine the part as it was still attached to its substrate, while with this substrate designed in a way that it could preserve the referencing points as you moved from the additive to the milling machine. So you have two topics. You have accessing their areas. You have stiffness, as you need a stiff structure, otherwise the part vibrates and deforms as you approach it with your milling tool. And then you need good accuracy in porting the part from one station to another, otherwise it's always a new reference operation again. And what you see here is the full workflow as we went really from the cut of the part to the final part in tolerance across different technologies. So you have on the bottom side a hardware flow with different machines involved, and on the and I can say it's mostly additive, milling, and then EDM for cutting. So at least three technologies involved. And then on the top side, you have a software workflow where, of course, you like to have the CAD of your part streamlined from the very first to the very end step, so that you don't have to import and export and re-reference your geometry again. That as an example, on the same line, we've developed multiple of these. I just put a collection of pictures here because we don't have the time to go in depth, but what you see here is, for example, a hybrid tire mold where we combined a machine substrate with some additive inserts that actually just bear the complexity, the required complexity where we need it. So it's a good compromise between cost and effectiveness of the solution. Some hybrid injection molding where we actually printed on top of an existing preform. So just to limit the complexity of the part to the additive region, and whatever is simple and that can be straightforward machined, we just kept it like that. Some hybrid cutting tool where again the topic was having a conventional substrate, which is the standard interface with the milling machine, HSK for instance, and the additive part of the component, which is the tool itself that bears the cutting inserts. I keep going. This is hip cups on the left, acetabular cups. printing them flat is relatively easy and also state-of-the-art. The question is to go in volume and automatize the machining. We ran a case study with this customer where we could actually print them in stacks and then feed them to an automatic Swiss type lathing machine, turning machine, where you have the bar that is automatically feeding each part to the cutting insert that takes care of machining the inside and then cutting away the external surface, which is what is keeping together the parts. And then a shoulder implant that is as built on the outside where we want it to be rough, and also we like to have a lattice on it, but on the bottom side, which is actually the side that is facing the build plate where we start printing, that's where we require machining. So the concept here was designing the supports in a way that they acted as a clamping fixture as we go into the milling machine. So these are just few examples of how you can conceive the final part since the very beginning of your engineering workflow, and try to really squish your mind, of course, having some knowledge with you in order to conceive the best solution for each individual case study. If there is volume behind it, then also automation may come in play instead of just manual labor, for instance, in loading the milling machine. Now, what I want to present a bit more in depth today is this case study, because I believe it's very relevant on the line of what I was just introducing here. Case study, actual case study, so reality. Customer came to us with the need, say, look, I'm a medical device manufacturer. I produce, in this case specifically, was spinal cages, which is a very common part, ongoing in production with additive. There's a lot of, he named over 1,000 different geometries, but there is commonalities among all of these, which are those that I listed there. So there's a conical nose, the bottom has to be smooth, and there's always a lattice. That's why we go additive with this part. That is what favors retention with the bone. And then there is on the other side an endo, that is where we connect the surgeon tool. So different shapes, very different to each other, you see them, but some key features that are common. And the question is, can I have something that replaces my traditional workflow, which is what you see here. As of today, and we're talking about, maybe I missed this information, but it's quite important, we're talking about over 100,000 parts a year of production volume. So this is really production. It's not prototyping, it's not testing, it's production. His problem is the traditional workflow that he has at the moment, that he used to have. Printing on supports meant for manual removal, and then finishing parts each one by one manually via a grinding tool. What does this mean? First of all, you have a topic of consistency and tolerance of tolerancing as a challenge on your part. Secondly, scrap rate, which he estimated between 2 and 5%, really due to a mistake, not on the additive machine, but by a manual mistake that you may have. Some parts are out of tolerance; they need to be scrapped, and then impossible to automatize. No, it's really manual, labor intensive. What we developed out of different concepts was a clamping solution that enables the parts, as they are printed, to go directly into a milling machine with a unique clamping. The principle is the following: any part, the part, however you choose your orientation, it needs supports. Why don't we use such a support and why don't we design it in a way that you can use that support as a clamping reference on any other subsequent machine. Thought about different designs, and finally we came to this one that is actually transversal to any, or let me say, a majority of parts. So what we show here is a spinal implant, but you imagine any part that you need as you print it and you cut it, that you machine, this is applicable. So we also applied for a patent on that is much broader than just spinals. The detail is the following. So you have on the support that is made solid enough so that you have stiffness there and some mechanical robustness. We applied these inserts that on the support are shaped as valleys. On the clamping jaw, they're shaped as peaks, and then as they meet together, they provide uniquely, and in the very moment you tighten the jaw, both referencing, because referencing is important, height and XY coordinate, as well as rotation angle, plus the stiffness and let me say the tightness that you need as you clamp a part that will be in touch with a milling machine, with a milling tool. What is the advantage? So first of all, the design is easy and straightforward, so the supports are fully printable, no extra complexity. We don't affect the additive time, because anyways we would have needed those supports. We actually do the function well of clamping the part, so warp is holding effectiveness is there. It's error-free, and it's also possible to reference correctly each part in a full automatized workflow. You don't have any part-specific tooling that comes with this shape, and therefore, out of all of this list of advantages is clear. The lower time is the cycle time is lower. And therefore the part cost, you gain in quality, meaning you lower the scrap rate because you just mill away instead of grinding, and it's fully ready for automation. So from the day you like to have, instead of one clamping part, instead of clamping one part, you put more, or you want to put a small robot that handles the part instead of a human, it's fully ready for that. So here a few examples, because not only we conceived it at CAD, but of course we had to prove it. This is what you have at simulation level, and then the reality. And here's the let me say the outcome of this test. We have roughly, this is titanium. We have roughly we analyzed 3 geometries, and we are always below 2 minutes of machining time on the milling machine. The benchmark was 3 minutes. That's what the customer requested, which is the average that is taking him to do it manually. Only on one case, on cage 20, the middle one, we were at 5 minutes of machining time, but in 3 axes. So with 5 axes, it can go below 3 minutes as well. With a proven reference accuracy of this clamping solution below 20 micron, that is definitely, let me say, compatible with what a milling machine requires in terms of position accuracy on this kind of geometry. So, and with this, I will wrap up. The principle is a bit broader than just the case I presented, but I hope I was able to deliver this key message. Post-processing, as we speak and as we collect feedback from market, is heavily impacting the unit part cost. So let's talk about how to make the process cheaper, but let us also talk about how to make whatever is beyond that cheaper, so that we actually grow more applications in a sustainable way. we as GF are experts in conventional machining, and we chose to integrate additive because we strongly believe the two go together, and only conceiving the workflow and the end part since the very beginning, you can have a successful applications where we can actually talk about volumes in a sustainable way. Of course, with all the advantages that additive brings. So lattices, complex features, all that we know. That was it. Thank you.